Okay, welcome to lecture 5.10, where I'm going to explain a little bit more, actually go into some of the mathematical details of Poole and Rosenthal's Nominate scores. Okay. Um, okay, first thing. Okay. Suppose we have a bill and a status quo. Okay. And for now, it might be good just to think of these as just scalars. These are both a number on a one-dimensional line, and if you like, in the nominate world, they don't force it. I was going to say they have to be between -1 and 1. The ideal points do, but the cut points don't. But whatever the case, some of these are just some number. They're scalars. And what we assume, there's bill and status quo, and legislator I votes B if and only if UI of B minus UI of Q is greater than or equal to 0. Okay, that's economics. If your utility for voting for B is greater than the utility for voting for Q. By the way, it's not the utility of B being the outcome. And the reason you got to do this, the same thing happened with Crable and Rivers' paper, that if they only care about the outcome, then if they know they're not pivotal, if they know that it's not a one vote margin, then it doesn't matter how they vote. You can't say what the utility is. You can't predict how they'll vote if all they care about the outcome is if all they care about is the outcome. So what Poole and Rosenthal assumes that the utility comes over how you vote, not what wins. Okay. Now, that is what happens in a non-stochastic world. Okay. Okay. In a stochastic world, Poole and Rosenthal assume that I votes B if and only if UI B minus UI Q minus epsilon, and this is for legislator I, and let's say B and Q, that's on roll call vote J, we might say on. So the error term for legislator I on roll call vote J, if that is greater than 0, okay, and so probability I votes B equals probability epsilon I J is less than or equal to UI B minus UI Q. Okay. All right. Poole and Rosenthal assume that epsilon I J is distributed standard logistic. Okay. So that means probability I votes B equals, and hope you remember from your homework, capital lambda, the stuff, the scene utility, or the how would you say that? The non-stochastic part. So anyway, it's UI B minus UI Q. Okay, must equal that. And if you remember, the form of that is just E to the UIB minus UIQ, all divided by 1 plus E to the UIB minus UIQ. Okay. That's it. Okay, that's the probability. Okay, now we haven't talked about how the functional form of these utility functions, what they look like, but we have talked about the error term involved with this voting. Okay, and so we're going to get these logistic type functions. Okay. All right. Next thing. Okay. Now let's talk about what the utility function looks like. UIB, UIQ looks like. All right. So let's talk first about UIB. Okay. If B is the bill, okay, we'll also have something for Q, but if we're just looking at one of the alternatives, there's a yay alternative and a nay alternative. If B is the bill, let's define xi equals i's ideal point. Okay. And then Poole and Rosenthal assume ui of B equals e to the negative b minus xi squared. Okay. Poole and Rosenthal. No, okay. Poole and Rosenthal say we assume Gaussian utility. Okay, now what does that mean? Okay, if you talk to physicists, when we say error terms are distributed normal, physicists call it Gaussian. I don't know why they use that term instead of saying normal, or why we don't say Gaussian. But what they mean, what Poole and Rosenthal mean, is that the shape of the utility function looks like a normal distribution. Okay, so if you graph this out, xi, so utility UIB would look like this. Looks like a normal distribution, okay? And in fact, if we had 1 over square root of 2 pi there, and we divided this by 2, it would look exactly like a normal distribution, okay? So they said those are just constants. The key is the shape of the utility function looks like a normal distribution. Now, lots of people see this, say, oh yeah, that makes sense. Yeah, we're making standard assumptions. Oh, normal distribution. No, we're not. Okay, normally we assume utility looks something like a tent or quadratic. This is a little unorthodox. You know, we make the normal assumption for the error terms. We usually don't make the normal distribution for the utility function. Poole and Rosenthal do. Okay, it's a little unorthodox. They assume that utility looks like a normal distribution. Now, what that means is sometimes some crazy things, okay? Here's one notion. Suppose that what that means is that if we had, say, a bill and a status quo, and suppose the bill moved policy to the left. Now, someone with a utility function like this might be indifferent, okay? Someone with a utility function like this would say, oh, I prefer Q over B. So this person is to the right. Okay, now, normally we think if someone, so the status quo is a little more right wing than the bill. The bill's making a movement toward the left. Normally, when this is the case, we would think, well, the more right wing you go, the more strongly you're going to feel that you should vote for Q over B. Well, that doesn't happen with Gaussian utility. So if we have someone with an ideal point way out here, someone really, really far right, his utility function looks like this, and B and the Q are in the tail, and Q would just be barely higher than B. So this is a little unorthodox. It says that if someone, you move the ideal point way, way, way down, all of a sudden that person's not going to care between the two alternatives. That's um, uh, a quirk about Gaussian utility, and that's why I think it's a little unorthodox. But regardless, that's what Poole and Rosenthal assume. Okay, so we've got we said something about the error term, said something about the utility function. Okay. Let's see. Now we do something similar, okay? If we were going to say how the person votes, let's talk about this. Let me go back. To say how a person votes, and say the probability that he or she votes yay or nay. So we got to fill in something for ui of b, ui of q, and do it in both those places. Okay. Told you here's what ui of b looks like. Okay. We'd have a similar term where we talk about ui of q. Okay. Notice ui of b, it's e to the stuff. Okay. Same thing for UIQ. So what we're going to have here is e to the, okay, UIB is e to some stuff. So this probability term is going to be e to the stuff, some stuff, minus e to some stuff, divided by 1 plus e to the e to some stuff, okay? There's going to be a lot of e, Euler constants, floating around in here when we do write out the Poole and Rosenthal likelihood function. Okay. 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 Okay, now more specific. Here's what we're going to do. Okay, so I said it's a bill and a status quo. Okay, it's not always that simple. Sometimes it's an amendment versus another amendment, or the amendment versus the bill. Okay, so instead of B and Q, what Poole and Rosenthal do is they say, let's have an alternative. We'll call one the yay alternative and one the nay alternative. Okay. Now, these are different. There's two of them on each roll call vote. We are going to label the roll call vote as J. So on roll call J, what we'll have is Z, J sub Y, and Z, J sub N. Okay. Now, so specifically, so ui of z, j, y is going to equal e to the negative z, j, y minus xi squared. Okay. And then ui z, j, n is going to equal e to the negative z j n minus xi squared. Okay, now to make things a little simpler, what Poole and Rosenthal do next is they take these terms. They say, well, the key is for determining the legislator's utility for a bill. We look at the difference between the location of the yay alternative minus the ideal point, or location of the nay alternative minus the ideal point, and you square it. Okay, we're in one dimension now. We're going to do the same thing when it's in two dimensions, but another way we can write that is just say zj minus xi. Turns out we're squaring it, so all we need is the absolute value of that. And Poole and Rosenthal say, well, really, all you need is the distance between that. So what they do is define djy. Let's see. How do they do that? Actually, dijy equals distance of yay alternative from i's ideal point. Okay, and then dijn, similarly, the distance of the nay alternative from i's ideal point. Okay. Given that, we can just rewrite these terms. Ui zjy just equals negative dijy squared. And then the same thing for the nay alternative. The utility of voting for the nay alternative is just negative dijay nay squared, where everywhere we have these d's, we'll just substitute in the distance zijy minus xi. Okay. All right. Now, okay, we have that. Now, okay, sorry, I should have erased these. Okay. Let's put these together. Okay. You know what? Let me stop there. You know, I think I want to do one more. Sorry. I'm going to do one more video. We're going to organize these blackboards a little bit better and do one more video to explain what the likelihood function will look like with Nominate scores. Okay, see you there. One more segment.